For part A, the answer is 400 joules per kilogram per Kelvin.
That is for part A. Fresh, what have you got? Fresh, what have you got?
Yes.
Fresh, unmute. Now look at my calculation.
Teacher, I've got 410 kilojoules per moles per liter.
You've got 410.
410.
Is it true? Now, I don't know whether you are able to see my screen. IV cam. Fish?
Teacher, we can see it.
You've seen what I've written?
Yes, teacher.
Yes.
I can get it.
Okay. So you are seeing where I'm writing on. Eh? Fish? Godi, can you see what I'm writing on?
No, teacher.
You can't.
Yes, teacher, I can see it.
I'm not seeing, I'm only seeing the question.
You are seeing the question only. Okay, let me first try to work on that one. Can you see? Pesh, are you seeing?
Yes, teacher, we're only seeing the question.
You're only seeing the question. You recheck again.
Teacher, I can see piece of paper, the answer sheet.
Yes. Pesh cannot see the answer sheet. Now, Godi.
Yes, teacher.
The question is saying that a sample of glass was heated to from 374 to 334. That means that we have our change in heat to be 314 minus 274. What do we get there? You get 40 joules, eh? 40 degrees Celsius. What is the mass?
It is 4 grams.
Huh?
4 grams.
4 grams. Huh? Huh? And what is the specific capacity of water? Huh? What are we looking for? We are looking for the specific capacity. And I've told you I've told you that we have quantity of heat equals to mc theta. Are you getting that? What is the mass?
Yes, teacher.
We don't know the mass. I mean, we know the mass, we know the temperature change. We don't know this one. So how do we get that? And they're telling us that 32 joules was the energy raised by the mass, which is 4.0 times the C times what? Change in temperature, which is 40. So that means that our C equals to 32 divided by 4.0, isn't it? Times what? 40. What do we get?
Yes, teacher.
Yes, teacher.
This is 0.2 joules per gram per Kelvin or per degree Celsius, isn't it? Are you able to see?
8.
So how did you get your 400 and plus? Have you seen my calculation?
Yes. Yes.
So what was the difference with yours? Yes, Pesh.
Teacher, I have seen my mistake. As for me, I didn't find the temperature difference. That's why I got different answers.
Okay. Godi, what was the problem?
Yes, teacher. As teacher, as for me, we used 30. Used 40 instead of 32.
40 instead of 32.
32. Yes, teacher.
You know, the question here is asking you to now get what was not given, which is the heat, isn't it? Huh? The heat was already given.
Yes, teacher.
It is the specific capacity which was not given. So can you now determine the amount of heat? the difference is 30. Eh? So that now we say quantity of heat equals to the mass, which is 4.0 times 0.2 times 30. And what do you get? So our answer should be 24 joules. I don't know whether you have got that.
Teacher, we got 24.
You got 24. So look at this. Now we are given the mass, the temperature change is 40, and then the specific capacity, the quantity of heat produced was 32 joules. So here the solution would be heat capacity equals to Q, which is the total energy, divided by the mass times the temperature change, which is 0.2. And then here we have already calculated our specific capacity. We know the mass because they have told you it's the same glass. And then we have the change in temperature, which is also given. And because of that, that also can help us to get that. So I think we can continue. I don't know whether you have a question.
Teacher, please place back the working so to finish copying the correction.
Which one? From the one I am writing from. Is it
Yes, that one.
this one? Okay.
Yeah, I've now seen it.
Okay then. What has happened to Margaret? I can't see her now.
Teacher, she's reconnecting.
Yeah. Okay, are we back? Yes, Godi, that's good. Pesh, are you there?
Yes, teacher.
Okay. Even part B? Margaret is very unstable. I think the network is disturbing. So Pesh, is part B also done? Okay. So let's move to the enthalpy or the heat content. Margaret, I'm afraid.
Yes, teacher, I'm back.
Did you do the other work?
Teacher, I'm back.
Have you done
The question?
Yes.
No, I have not yet done part B.
You've not done part B. What was your answer to part A?
Teacher, it was 0.2.
0.2, that is correct. So you want to do part B?
Yes.
Do you have the question?
No?
Okay, I'm giving you 2 minutes to finish that. You can see it on the screen?
Yes.
Okay, 2 minutes to finish that. Is that done?
Teacher, not yet. I'll finish it later. We should continue.
Okay. So let's look at enthalpy. So enthalpy is actually described as the energy absorbed as the heat content during a chemical reaction at constant pressure, and it is represented by delta H. So what we are talking about here is that you have some potential energy in a compound. For example, we have said carbohydrates are energy-giving foods. Now we want to find out between rice, posho, kalo, cassava, which one usually contain the highest amount of energy stored in their bones. Now, that means that we are required to burn completely same amount of any of those food substances. In human beings, we now burn them under aerobic respiration or in animals. But in a laboratory, we can also burn them completely in a calorimeter. Once it is burnt, then we measure the amount of heat it generates by how much temperature does it raise a specific amount of heat when we subject them to water. So that heat content can be termed as the enthalpy. Enthalpy is the heat content actually. And in chemistry, we represent them by symbol H. So we cannot measure that heat content. We actually can only measure the change in the content because we're talking about how much is produced and we cannot measure it directly. So we have to again use it to heat a known volume of water such that we find out how much heat is produced when this one is completely burnt and transferred to that of water. So the amount of heat produced by water is what now eventually we call the total heat change produced by that given mass of the fuel that is used. So an enthalpy change is therefore the amount of energy absorbed by a system as heat during the process. But remember, it must be at constant pressure because pressure changes the heat content. So the pressure must remain the same. So where is what we call a thermochemical diagram. Now the thermochemical diagram tells us whether the change is exothermic or the change is endothermic. For example, when you look at this thermochemical diagram, which I hope you are all seeing, there is a potential energy, and then there is a reaction path that you can see. Now, you see at this thermochemical diagram, the reactants are at a higher energy than the products, meaning that in this kind of reaction, if products are supposed to be formed, then the temperature must be reduced. So in this reaction, the energy of the reactants must be higher than the energy of the products. So that is a thermochemical diagram. Now, when you look at this, we are saying that the minimum energy required to start the reaction is denoted by EA, which we call the activation energy. Now, this is the energy rise. For this reaction to occur, you must place there some small energy. I've told you, for example, if you want charcoal for cooking, there is no way you're just going to put charcoal and then charcoal starts producing the heat. You must provide the minimum energy. That's why you have charcoal lighteners. That charcoal lightener just ignites. And then as the bonds between the components of the carbon in charcoal starts breaking, it releases their excess energy that was stored in the bond. And it is this minimum energy that you need in order to raise that energy. And actually it is represented by symbol capital E, A. Now, once that has been overcome, it means that now all the bonds are broken. Then we have a bond formation. And therefore the products will actually absorb the heat such that there is going to be minimal energy that is stored in the products. And that is the reaction coordinate we are talking about. But we are going to look at the details about that. So what is activation energy according to you? According to this diagram we are seeing. Then you tell me, is this reaction endothermic or exothermic as represented by this energy level diagram? Is somebody here? Again, no? All of you can't hear me? Margaret. Can you see the screen now?
Yes.
Unfortunately,
Yes.
it is raining here. I don't know whether it is the one affecting the network. So my question is, can you hear me? Godi, can you hear me? Patience, are you hearing me? Margaret, can you hear me?